All right, this is a video for geometry on inequalities in two triangles. So we'll be using a couple different theorems here to compare two separate triangles to each other. And the two theorems we'll be working with are the hinge theorem and then the converse of the hinge theorem. And we'll start off with an introduction and then do a few solved examples. So the hinge theorem says this: if we have these two triangles, triangle ABC and triangle XYZ, and if we know a few different things, we need to have two pairs of congruent sides. So what I'm going to highlight in purple, and then what I'm highlighting in green. And then secondly, we need to know something about the angles connecting those two sides. Okay. If you've worked with triangle congruency, this is called a side angle side scenario, but you may not have worked with triangle congruency yet. But what's important though is that the angle that we know information about is the angle that's formed by the two pairs of congruent sides. Okay, so if we were working with these angles up here, we wouldn't be able to use this theorem. Okay, so that's the setup. If we know all that, and then if additionally we know that angle A is larger than angle X, we can conclude something pretty important here. Therefore, BC is larger than YZ. We're not able to conclude exactly how long BC or YZ are, but all we know is that BC is larger than YZ. I try to remember this by thinking of these as rubber bands. And it's called the hinge theorem because we can think of this angle as being a hinge between maybe two solid pieces of wood or something. And I think it's pretty intuitive to imagine if you were to open up that hinge, the rubber bands would stretch and side BC would be longer. All right, so let's use that hinge theorem and see what we conclude about this pair of triangles. So we have triangle SAK, which is a right triangle, and then triangle UOY, which appears to be an acute triangle. It does have an angle of 70 degrees. So let's see if things are set up properly. So we have a single tick mark side, which is good, and then a pair of double tick mark sides. And then also it looks like the angles that we're being given are the angle formed by the intersections of those two sides. So that's all good. So since that right angle at angle A is larger in measure than angle O, what we can conclude is SK must be larger than OU. Okay? And that's pretty much all we can conclude at this point. SK has a longer length than OU. There's a interesting real-world connection. This is maybe a little bit goofy, but super intuitive. But it's an interesting connection between what we just did and a real-world experience. So I hope you can imagine you're in an amusement park. You're on this hanging ride. You're sitting at point C, and the top of the rope going down to you is at point B. And then this ride spins around with the radius of spin being roughly point A. And we're just curious, as the ride starts spinning, are you farther or closer to point A once we know some information about angle 1 and angle 2? So angle 2 is larger, okay? And so we can conclude that at time 2, you were at a larger distance from point A. And again, intuitively, it makes sense. You're being swung out from the center, right? But the hinge theorem sort of formally tells us that that must be true because angle 2 is larger than 1, and the lengths of AB and BC don't change. They're consistent lengths, right? So the only thing that changes is the length of AC. Converse of the hinge theorem is just like the converses we've been working with. We can flip the order of the conditional statement. And in this situation, we have the same setup, except we know that one side is longer than the other side. We don't know anything about the angles yet, but we know that one side is longer than the other. So we can make a conclusion, though, using the converse of the hinge theorem. We can conclude that angle A, the measure of angle A, must be larger than the measure of angle X. Okay, so that's our conclusion. If we know that the sides are unequal, the angle measurements would be unequal in the same direction. So this is a little bit of a harder problem we'll do to apply this, finding possible angles. And it looks like we have a quadrilateral with one diagonal drawn. We have two side lengths known, 15 and 10. And then we have one pair of congruent segments also. RU is congruent to UT. And we're just trying to find the range of possible values of X is our goal here, our task, the range of possible values of X. So it looks like we have two triangles that we're working with, so we can try to apply the hinge theorem. One thing to know is side length US shows up in both triangles, so that's effectively the second pair of congruent sides. And then if we want to think about the rubber band that I was talking about earlier, the 15 is larger than the 10, meaning the 60 has to be larger than that 5x minus 20. So let's go ahead and write that out. We can say that 60 is larger than 5x minus 20. We can add 20 to both sides. 80 is larger than 5x, and divide both sides by 5. 16 is larger than x. And then I'll just flip that inequality around. If 16 is bigger than x, x has to be smaller than 16. The fact that the 15 is exactly 1.5 times the 10 doesn't really get us much. It doesn't allow us to actually solve for exactly how large that angle must be. All we're using is the fact that 15 is simply larger than 10. There's actually something else we can do. That angle has to be greater than 0, right? So we can additionally say that 5x minus 20 has to be greater than 0. Add 20 to both sides. 5x is greater than 20. Divide by 5, x is greater than 4. So we can combine these two results together into one statement. X has to be bigger than 4, meaning 4 is less than x. And then x additionally has to be less than 16. So that would be x written as a compound inequality. So that's angle or triangle inequalities when we're comparing parts and pieces of two different triangles. And we got through it, and that's a good place to stop.